Good morning. Sorry, I thought I sent the link, but I didn't. So, but anyway. Oh. So there's something with my email then. Okay, that's fine. Right, so we continue on section 10.8. So section 10.8 just like a summary, actually study a bunch of tests, and so pretty much review the conversion test that we have 9 of them in total. And this is what we're going to use in the strategies. Diversion test will be the first one, because if the n term, if the k term go to 0, inconclusive. If it go to something else other than 0, it is divergent. And then the limit comparison test. This list is very important. So with this, we can turn a series into something very simple to compare to. And then the ratio test, alternating series test. Alternating series test, when we see the -1 raised to some power, that we know. An alternating series. And then the root test and the integral test. So the first one we have is this one. Determine if this series is convergent or divergent. So the first thing we check is we find the limit of the n term when the k goes to infinity. What will be the limit of that? So the limit of this according to that ranking, of course ln is bigger than a constant, so we just take the ln and then we find the limit of that. It is something other than 0, so that is divergent. Next we use this one. We have this series, and first thing we find the limit when k go to infinity, and it is equal to 0. So it is inconclusive, meaning that we cannot do it using the diversion test. So we'll try something else, and that's something else. We certainly can use the integral test for this one, because certainly we can integrate this. The only thing that I prefer not to integrate this, because integral tests usually will have a lot more work than the others. Right. So the second one on the list is the limit comparison test. So pretty much what we compare to is just ignore the power, take the one with the highest power, and this is the series that we will compare to, 5 over k. By the way, in your homework on my math lab, when we say we compare that series to this series, we can also, instead of using this one, we can also use (1 over k), meaning that the constant really doesn't matter. We can just replace that with 1, and that still work. Oh, actually wrote that down earlier. Sorry, we already have that. Yeah. So the constant really doesn't do anything. So take the one with the highest power on the top, highest power on the bottom. By highest power, now we are standing to this, the one with the highest power, with the higher, I should say, the term that is more significant, the term that go to infinity faster, will dominate everything on the left of it. So we do that. And then don't get too hung up with the part that we have here. The next three lines here are not really important. The most important part here is when we have the series that we compare to, and we just find is that series convergent or divergent, and then if it is convergent, the other series is convergent. If that is divergent, the other series is divergent. So in this case we have B sub k is divergent, therefore A sub k is divergent as well. And the part that the three line that we do here, it just show that the limit of A and K, A sub k and B sub k equal to a constant, meaning that they are comparable rate. Remember, if the top is too big, go to infinity faster, this will go to infinity. If the bottom is going to infinity too fast, this will go to 0. Now if they go to something else between 0 and infinity, that means they have comparable rates. So they go to infinity kind of at the same rate. Because of that, if it is convergent, the other one is also convergent. If it is divergent, so is the other one. Right, now we go to 3. Now we have this series. Right. So again, the checklist, diversion test, check the limit when k go to infinity. If it doesn't work, try limit comparison test. However, usually if the problem we see -1 raised to the k power or -1 raised to the k power, k plus 1 power, pretty much every time we see this -1 raised to some power, k or k plus 1, that is the alternating series test. Because the sign here alternating, if k is even, it is positive. If k is odd, it is negative. So every time we see that, that's the alternating series test. Now, without that term, we'll have A sub k equal to just 1 over k squared minus 1. Right. So once we recognize that we're going to use the alternating series test, just ignore the alternating term, and that's what we have. Right. For alternating series test, we test two things. First, is A sub k non-increasing? And so we check. So that there are different ways to show that it is non-increasing, or we show it is decreasing. We can check derivative. If the derivative is negative, it is decreasing, and decreasing is non-increasing. That's one way to do it. The other way, we can show that as k increase, A sub k decrease. So that's simple, right? for this. So as k increases, the bigger the k square minus 1, the denominator, the bigger the k, the bigger this is. So if that one increases, this one is increases. However, if the denominator increases, the whole quotient will decrease, because we have a finite amount. The more we have to divide by, the smaller we have. So therefore the whole thing decreases. If we can do that, it is much better than taking derivative and having show that it is derivative is negative. Right. So k increases, k square minus 1 certainly increases, and then the bottom increases, the top is constant, so the whole quotient decreases, and decreases meaning that it is non-increasing, so that check. Decreasing is non-increasing. Right, so that's the first thing. The second one we check is that term goes to 0. As k go to infinity, is this one true? So we track the limit. Once again, k square, that power is bigger than constant, so we're just going to take that. And that's simple enough. Let's put infinity in. A finite divided by infinity is 0. So the limit equal to 0, and that check. Since both of these check, we say that the series is convergent. If one of them fails, the series is divergent. So this one clear. When we see that, alternating series test for sure. Right, next. Number 4. So on this series, there are a lot of tests that we can use. Certainly the integral test can be done, because if this is the integral, we can integrate this using integration by parts. However, it would be a lot better if we take the e to negative k, move it down to the bottom, becomes e to the k. Right, so we're going to try to find a test to test this, and a lot of way to do this. Limit comparison test, diversion test. So let's try that first. So first, this is the diversion test. check the limit of that term. So let that term be h of k, and we take the limit as k go to infinity. Right, so limit of that. Right, the first rule of the limit, by the way, just one term on the top, one term on the bottom, so we're not gonna go back to this and delete some of the terms. What we actually look at this is we have exponential. By the way, if exponential is e to k is classified into this, we have a constant base raised to the exponent, and the exponent is changing. So in this case, that one is e to the k, and the k is like k to the first. So this problem, we have the k is this, the e to the k is this, so the e to the k goes to infinity a lot faster than k. So if we have a term at the bottom go to infinity a lot faster, the whole thing will go to 0. So this limit equal to 0 without even doing anything. However, if you actually want to do it, first thing is try to put in the limit and see what happens. Right, so we have that, which is infinity over infinity, and that is indeterminate form. Right, indeterminate. So we can use the Hospital rule. Which means taking derivative of the top and derivative of the bottom. Derivative of k is 1. Derivative of e to the k is same thing. And then we put infinity into k again. E to infinity is infinity, and once again, finite divided by infinity is 0. The bad thing is divergent test. If this is equal to 0, it is inconclusive. So that doesn't work. So let's try a different test. Limit comparison test. Yes, certainly this one we certainly can compare to some limit, but that would be difficult to do the limit comparison test. Alternating series test, we're not going to use alternating series test because we don't have the -1 raised to a power. So not alternating series test for sure, because they're not alternating the size. Limit comparison test, yes, certainly we can do that, but difficult if we come up with the series that we compare to. So for limit comparison test, we actually have to find the other series. We cannot really do anything because that is simplified already. Usually when we do the limit comparison test, we have something, let me just show you real quick. We have something like this. Then the limit comparison test, we just ignore this term, we can compare to it. Like this, ignore this term and ignore that term, then we can compare to it. So that's why we can use limit comparison test on those examples. But on this one term on the top, one term on the bottom, cannot really compare that way. So not limit comparison test, alternating series test doesn't work because there's no alternating term. So try the ratio test. So what is the ratio test? The ratio test say that, by the way, we use ratio test where we have those things, and suddenly e to the k is classified into those. Right. So we just check the ratio of consecutive terms, and then we have those cases. So for ratio test, let R be the ratio as k goes to infinity, and that ratio is we have to throw in absolute values a sub k plus 1 over a sub k. So the next term divided by this term. So absolute values. So first we're going to put k plus 1 into k and into k. So we have k plus 1 over e sub k plus 1. So that is where k plus 1 substitute to k. Now a sub k at the bottom will be the same. Right, so that's what we have. Divide fraction is multiply reciprocal. Multiply reciprocal, e to the k on the top, k at the bottom. Right. By the way, k go to infinity, so that positive, e to the k suddenly positive. So we can just drop the absolute values. Right. Just drop the absolute values. Right. K plus 1 is still k plus 1. E of k plus 1 is e to the k times e to the first. When we multiply them, we add the exponents. And then we have e of k and then k. Right. Let's write a little note here. Since everything is positive, we don't need absolute values. We don't need absolute values. Right, and then what we can cancel from here is e to the k, cancel e to the k, and we end up with, on the top we have k plus 1, the bottom we have e to the first, which is e, and then k. Now, finding limit, the constant 1 doesn't matter as k goes to infinity. So the top we just have k, the bottom is e times k. Once again, we can cancel out the k. And so we have 1 over e. Right, so what is 1 over e? 1 divided by e. So that is less than 1. So if it is less than 1 in the ratio test, it is convergent, absolutely, or just convergent. So the series is convergent. Yeah, because it's less than 1 for ratio test, it is convergent. Right? So usually if we just have a term on the top, a term on the bottom, we don't use limit comparison test for that. So we don't use limit comparison test for that, because just one term on the top, one term on the bottom, it will be kind of difficult to come up with the term that we compare to. But for something like 4 and 5, I mean from 5 and 6, definitely we can use limit comparison tests. So keep this for now. Alright, next. Number 5. Right. This is e times k, not e to the k, because e to the k here cancel with e to the k, so we just have e to the first power, which is just e. So this is e times k, not e to the k. E to the k cancel out. Maybe not very clear to see. Yeah, that cancel out. So e to the first, which is e left, and then that's just e times k. Right. So for this one, when you get used to it, you can see right away if that goes to 0 or not. So, but I said it's useful. Just trying to take a look at the divergent test. If we let a sub k be that term, right? And we'll find a limit for that. And when we're trying to find a limit, this will come in handy. 3 to the k, 5 to the k, those are b to the k here, because that's a constant raised to a constant power. Alright. I mean k is the index. Alright, so we take that term, we take this term. Because the 1 doesn't matter. 5 to the k is too big, minus 1. Right. I make this problem, so technically this one will work correctly if we start at 1. because if you put 0 for k, 5 to 0 power is 1, 1 minus 1 is 0. I don't want to divide by 0, so this should be 1. Yeah, so please change the limit to 1 to make this sure that this is not 0. Make sure that we don't divide by 0. And changing the lower limit, changing the index, missing the 0 doesn't matter. In terms of convergent and divergent, missing the first term doesn't matter because we have infinitely many terms. Right, so we do that. So what's that equal to? Since both of them are raised to a k power, so why don't we bring them inside? And we have that. Now what is that? So 3 over 5 like 0.6, right? Now of course we have 0.6 raised to some power. The bigger the power, the smaller the number. And eventually, as k increases, this will go to 0. Or either write that or we write equal to 0. By the way, if you go to section 10.2, that is the geometric sequence, and k, the ratio less than 1, so that's 1 equal to 0. If that 1 equal to 0, divergent test is inconclusive. Right, so the first test I usually go to, it doesn't work. So next, limit comparison test, ratio test, and alternating series test. Usually those are the three tests that we're going to do next. This is not alternating series because we don't have the -1 raised to the k power, or we don't have the -1. We don't have the alternating terms. All of them are positive, so the sign do not change. Cannot use alternating series test. So either the ratio test or the limit comparison test. And this time we go to the limit comparison test simply because when there are more than one term on the top and bottom, usually limit comparison test will work. And for that, we're going to let b sub k equal to that, but we're going to use this list and ignore anything that is less significant. So I'm just going to take 3 sub k and 5 sub k because the -1 is not significant. I should write this. Since 5 to the k go to infinity a lot faster than a constant 1. So we only need 5 sub k and we don't need the -1. And yes, so like I said, usually if there are more than one term on the top and bottom, the limit comparison test usually is the good choice. Right, now we have that. Now the only thing need to determine is this one convergent or divergent? Yeah, we can go 0 or 1, doesn't matter. And so we consider this series, both of them under the power of k. So we'll bring that inside. As the power of k. Now, this, and also a note, usually when we use the limit comparison test, what we actually compare to. So, when we use the limit comparison test, we usually compare to the p series, p greater than 1 convergent, less than or equal to 1 divergent. This one, when we have something raised to the k power, and that's something, the ratio in this case is 3/5. So we're going to use limit comparison test and compare to geometric series. Yeah, compare to, cannot really see that. So this is a geometric series. Where the ratio is equal to 3/5. Now, if the absolute values of the ratio less than 1, it is convergent. And since absolute values of R is 3/5, less than 1, B sub k is convergent. Now, if B sub k is convergent, so is A sub k. I will write out A sub k. Yeah, so that's why the limit comparison test is very nice things. When we have a few more terms on the top and bottom, just ignore what is negligible, and then we just find out what is that series. If that is convergent, the original series is convergent. If this is divergent, original series is convergent. So it's not that bad, right? Yeah, just one tiny little things here. It's not that big though. To actually complete limit comparison test, we still need to show that A sub k and B sub k go to 0, go to infinity as a compatible rate. Growth, the growth rate of A sub k and B sub k are compatible. Therefore we use the comparison test. Let me zoom out. Right, we see the whole thing. Right, and to show that they have the growth rate are comparable, we just show that limit as k go to infinity of A sub k over B sub k equal to a constant, and by that constant I mean anything between 0 and infinity. So Divide this is multiply reciprocal. And then when trying to find the limit, that minus 1 is negligible, so ignore that. And everything cancels out. I'll just have 1. And so just need to show that the limit of AK and BK behave the same, or I say the growth rates are comparable. So this is equal to 1, which is finite. By finite I mean between 0 and infinity. So yes, that check. By the way, that is the complete proof. Usually, let me zoom back in first. Usually, on my MATLAB or the homework, we only need to do this part. The part that's showing comparable rate, we're not doing much. So remember this. This is the growth rate, ranking of the growth rate. Whatever on the right is significantly bigger than whatever on the left. So if we're going to use the limit comparison test when we have a bunch of terms, we just ignore anything that is on the left of this. And if that is the case, you just ignore in terms, you don't make in anything up. We don't even need to show this part. Don't need to show this part here, because we're still keeping the highest term, the term that grows to infinity the fastest. So in that case, we do not change anything. The comparable rate A sub k and B of k are comparable. Once again, if we have a ratio of two things, each of them have a bunch of terms on the top, a bunch of terms at the bottom. Using this ranking, knock out anything that is negligible. That the new series, the new sequence, is comparable rate to the one that is before. So unless we make something up into it, that's different. I'll go to that part later. Right. So now, number 6. Let's just make something while I'm just going to add square root of k here on top, and at the bottom let's just add sine of k into it, or cosine of k, doesn't matter. Alright, just at the bottom like this. And usually when this is the term, when we try to find the limit for the divergent test, just look in this ranking. Right, k square bigger than constant, that constant 3 is negligible. The square root of k is equivalent to k to the 1/2, that 1/2 power is less than 2, so also negligible. Take the one with the highest rate, k square. At the bottom, k cubed is bigger than k is bigger than 1 and bigger than sign of k. So we check the one significant on the top, significant at the bottom. Reduce that go to 0, so that doesn't help. So for the diversion test, if we need to do it, I'm just gonna write down real quick. If we want to find the limit as k goes to infinity of h of k, that is the same as we just set the highest power on the top, highest power at the bottom, or the highest rate on the top, and the ranking of course is here. Like I said, when you take the test, make sure this is somewhere close. Preferably you memorize that already. Right, so this we have 1 over infinity, which equal to 0. Equal to 0 for divergent test is inconclusive. It is kind of like the one on the note, but I just make it more complicated just to show that it doesn't matter what we add to it, as long as those terms are less than the highest rate. It doesn't matter. I can add a lot of this. If I want to, I can even add the ln of k to it, because adding ln of k to it, that is significantly less than the power. So ln of k is less than power of k. So adding that in does not change the problem at all. So that's my point. We can have something complicated, but only the one with the highest rate will determine the behavior of the term. So that's why I just make something different. Yes. Right. And also, usually when we have a bunch of terms on the top, a bunch of terms at the bottom, we don't want to use the ratio test because that's complicated. Ratio test usually just one term at the top, one term at the bottom. So in that case, why don't we use the limit comparison test? That's where we have the bunch of terms. So for limit comparison test is where we have something that big, and limit comparison test allow us to ignore everything else that is negligible. Sorry. And let b sub k be a series my brain is faster than my hand on that. This example. I said b sub k. B sub k is comparable to that one. Therefore, we ignore all the negligible terms. So that just be k squared over k cubed. Right. In this case, just 1 over k. Just want to bring up one point. Let's say instead of k square, you have 2k square here. Even though if there's a 2, it doesn't matter. We can just choose 1 over k. My point is, if there's a constant multiplied to it, we can always just ignore that constant. Actually, we have two examples. I'm going to do that quickly. Right now, what happened to that series? What happened to this series at k for 1 over k? Right. So we see this series actually on every section, and so what's this series? 1 over k usually when we do the limit comparison test, we either compare to the geometric series. In this case, we compare to a p series where p equal to 1. And according to this, where p equal to 1, it is divergent. Less than equal to 1 is divergent. So this is less than equal to 1, which is divergent. And since b of k, the series b of k is divergent, this series is divergent as well. So that's the powerful. That's why the limit comparison test is very versatile. We use that a lot. Right. Now I just want to bring up some quick example in relation to the two examples we just did. Let's look at this one. I'm just going to make up something real quick. If instead of this problem, what we have is something like and that, and we go compare to let's do that. Let's say we have this series, and if we have to do it, the series that we compare to just ignore the term that is negligible. K square that is bigger than cosine. Cosine just between -1 and 1 really didn't do much compared to the k square. So in that case, we're just going to take 3k square on the top, and the bottom k to the 4th, and ln of k power is going to be bigger than ln of k. This is the ranking. So, and when we choose b of k, we can even ignore that constant multiplying here. So in this case, when we reduce, we would let b of k equal to 1 over k square when we simplify it. So if we want to use the limit comparison test for this example, we're going to use this term for b of k. So if there's a constant, just ignore it. It doesn't affect the problem. By the way, 1 over k square, this is a p series where p is equal to 2, bigger than 1, which is convergent. Right, so just want to show a quick example what would happen if we just change the problem practice. Right, just want to go back real quick to this problem. Now if we just switch things around ever slightly, instead of 3 we have 6. Still we do the limit comparison test, so we compare 2. Again, that bigger than 1, and then this is 6/5 to the k power. So the series, this is a geometric series where the ratio is 6/5 bigger than 1, so therefore this one divergent by the geometric series. So if that one divergent, the original series is also divergent. So those are the I'm sorry, which one? Talking about this one. Oh, this one. Yeah. So what I'm trying to say is, if it is a geometric series, we can also use the limit comparison test, and this one is less than 1, absolute value is less than 1, convergent, absolute value is greater than 1, divergent. And so the limit comparison test, usually we can compare to geometric series or a P series. Right, take 5-minute break. We continue at 9:07. And also the way the stream setup, I try to use the normal latency, so it has like 25-second delay. So this one. Not really. When we do the comparison here, remember, I mean, this is the list when we do the comparison. This is for k go to infinity. We compare here. What we actually compare is the row rates. So which one go to infinity faster? Oh, this one. Alright, yes. Sorry, like I said, it has like 25 second delay, so it takes longer time to communicate. So on this one, yes, the reason the 3 doesn't matter because that constant, and we have 1 over k square. By the way, when we just think about this, we don't actually look at the index though. The problem, we might have the problem that start with 5, it will not change the problem, because what we actually worry about here is what happened for the whole series. But the whole series meaning going from whatever term doesn't matter, but we have indefinitely, it goes on for indefinitely. So having k equal to 1 or the first few terms doesn't matter, could be equal to whatever the numbers is. Yes. And when we have b's of k here, what the next step is, actually we don't compare to b's to the k, we compare to the series of b's to the k. In which case what we have is that, and this is the p series. With p equal to 2, and this is bigger than 1, so it is convergent. Yeah. And so we, as you see in this kind of problem, we don't even pay attention at the index. At the bottom, whatever we start with, we don't really look at that at all. It doesn't matter where we start, it just happened to whatever terms we have. Yeah, so the lower index usually play little or no role at all. If it is convergent, missing the first term is still convergent. If it is divergent, missing the first term is still divergent. It doesn't change anything because we have infinitely many terms. Missing the first few terms doesn't affect anything at all. Right. Especially, yes, in that case, pay attention to this. That is the p series. Oh, I see. The reason I put 1 here, because this one, k is the same as k to the first power, not because of the index 1, right? Now I know where the confusion is coming from. Yeah, I'm not using the k equal to 1 here. The reason I put 1 here because k is equal to k to the first power. Yeah, that's why. And also you can say that this the sum of the series 1 over k, this is called a harmonic series. So when we have 1 over k, that is divergent. Or we could just say the p series, p equal to 1, less than or equal to 1 is divergent. Yeah. So, yeah, go to the p series. It is not the power series, but we could say that that p stands for power. By the way, power series is completely different things. This is in the next section. We will go to that in a few minutes. Right. I think we'll just do two more, then go to the next section. I don't want to stay too long here. Right, so what do we do here? So first thing, once again, diversion test. That's the first thing I always whether we write out or not. That should be the first thing we check. I take the limit of that as k go to infinity. So how do we find the limit of this? So usually where we have sine, cosine, those are bounded functions. So when we just divide by k to the 3 halves over 5. Then we divide by k to the 3 halves plus 5 on both sides. So that's what I should say. For that. Now as k go to infinity, this one go to 0, this one go to 0, the middle go to 0. As k goes to infinity, I just take the highest power on the top. And ignore the 5. Because k to the 3 halves is significantly faster to infinity than 5. And we have negative 1 over infinity to the 3 halves. Finite over infinity, so that equal to 0. Similarly, that one go to 0 as well. So the left go to 0, the right go to 0, the middle go to 0, and that's what we call the squeeze theorem. By squeeze theorem, that's the limit. Which actually doesn't help at all, because that is diversion test equal to 0, meaning inconclusive. That doesn't help much. Alright, however, as mentioned before, usually when we have more than one term, the limit comparison test will be helpful here. So what do we let b of k equal to? What we let b of k equal to is, we look at the original problem, ignore anything that is negligible. So for sure at the bottom we're going to choose k to the 3/2. But the cosine of k, yeah, what values do we choose for that? And because cosine is between -1 and 1, I'll choose a different color. Because of that, we can just choose one, and we can use the limit comparison test to this. However, this I'll have to say that because cosine of k less than 1, so let's write this. Since cosine of k less than or equal to 1, divide both sides by k to the 3/2. Yeah, so certainly you can compare like that. And next, limit comparison test, usually we compare to, I don't know why I write that in red. Now we consider the series b of k, and this is k 1 over k to the 3/2, and this is again is a p series, and p equal to 3/2, which is greater than 1. That's why this is convergent. So since b of k is convergent, a of k is convergent as well. Yeah, so again, that is the p series. What is also very important for the limit comparison test, we actually have to show that a of k over b of k equal to constant. We're not going to do that here, but I'm just going to write a note here. Still need to show that. Actually, I'm just going to have to do it. is finite. By finite meaning between 0 and infinity. So that's very easy to do. A of k over b of k. And once again, when we see cosine, we can use the Sweet theorem again. But when we do this, is whatever the limit here is, that's going to be less than infinity, so which is finite. Yeah, so kind of difficult to find the limit. And sorry, the problem is not that complicated though. Just compare to this and it's convergent, but there's a lot of things that go along with it. What we can also do is the direct comparison test. Or just comparison test without the direct. I call it direct comparison test, but in the book they just call comparison test to distinguish with the limit comparison test. So what we see here is, I'm going to write this out again. A of k equal cosine of k to the 3/2 plus 5. B of k is 1 over k to the 3/2. And since A of k less than or equal to B of k, the series also less than that series, but B of k is convergent. Anything less than convergent is convergent. So this series is less than that series, and B of k is convergent, so is A of k. Yeah. Unless of course we're talking about because cosine of k have so without going too much into this, which we already did, when we have sine cosine, we can just replace that with one kind of, and then we do compare. When we have sine cosine, replace that with one, and we can do the limit comparison test. That will save you a lot of trouble. Right, this one, because we have the -1 here, this definitely alternating series test because of the -1 power. Doesn't matter if it is k minus 1, k plus 1, k plus 3, doesn't matter. The -1 raised to some power where it's changing from positive to negative. So that one is alternating series test. This is telescoping because they will cancel itself. And this one is the root test. We haven't done any root test, so we just skip ahead and go to that point. That's one. Sorry. There's a lot can be said about this problem, so that's why we spend a lot of time on this. But what I'm trying to say is the direct comparison test, sometimes we don't use this a lot, but we can just use the limit comparison test also work just fine. I'm sorry, I promise I will not talk about this anymore. Right, last time. Right, the only thing that could be potentially be a problem to this one is cosine of k could be positive, could be negative. So in that case, to be safe, I would put the absolute values into it and then use 1, and this will work out perfectly. So what I would do is, for this problem, we can also do just slap the absolute values into it. And we do the same thing. This one is convergent with the absolute values. It will convergent without the absolute values. So sometimes I slap the absolute value to it and say that will be less than 1. Yeah, because cosine is less than 1. Absolute values of cosine is less than 1. Yeah, and it is absolute convergent. So therefore, it will convergent without the absolute values. Fine. So, and that's a lot we can discuss on that problem. Now just go ahead and we just need to do one problem with the ratio test. I mean, we did that, but we just want to do one problem with the root test. And the root test is very distinctive. Where we see something raised to the power, we're going to use the root test. Where the whole thing raised to some power, that is the root test. So the root test, taking the limit as k go to infinity of the root k. Right, the root cancel the power, so this will have just that. So the root test is useful because the root test will cancel the k, and when we see that very distinctive, we use the root test. Right, divide this, we did a bunch of this already. Highest power at the top, highest power at the bottom. And that's just 1/2. Limit of 1/2 is equal to 1/2. And similar to the ratio test, if this is less than 1, it is convergent. Yeah, the root test. Yeah, less than 1, it is convergent, absolutely, or convergent. Right, with that, we'll go to chapter 11, power series. maybe. Right, the first part. Approximating function with polynomial. Let me change the section. Right. So now we go to kind of different thing. The focus now is not convergent or divergent anymore. The focus now is what do we do with the series? Why is that so important? Right. And more importantly, why do we study that in calculus? And to be honest, I told you this already. Back when I took Cal 2, it was in the 2004 at Eastfield also. After I took it, I could say a few weeks later, the series and the sequence, that's the first thing I forgot. So, because Cal 2, they have a lot of different things in there. Even though you go to Cal 3, you're not using a lot of the, I should say you don't use in any sequence and series at all. So it's very, very easy to forget the power, the power series and the sequence and the series. So because of that, rather than go over every single thing here, we cannot really focus on everything. So I try to focus on what is really important in this chapter 11. I would say about only a few things that really important that we need to know. Other than that, it's not as much we can do. Unless we practice a lot. Right. So a power series, usually series without mention anything, it is an infinite series. And called the power series is a series of the form. So it is a power series, so we definitely has the power. Potentially we might have some constant in front of it. But that power make the power series. By the way, we call this the power series. This on the reciprocal is called the P series. Yeah, so this P, even though it is for that power, but we don't call that power series. That kind of, I guess this is okay. If you write this as 1 over k, then yes. Sorry, that's different things. I'm confusing myself. So the difference between the P series and the power series is that the k here is at the base, the k here is on the exponent. So let me write out the note important. Index k is on the exponent. That's what makes it a power series. So whenever we have x, or we might have something instead of that. We might have x minus something, and that index is also on the exponent. So when we have that, we call that a power series. CF cases coefficient. And A we call the center. A constant. So the index doesn't really matter. The constant doesn't really matter. What makes it power series is the power term, meaning the index raised to the power. Compared to the P series, 1 over K, the index at the denominator and the base of the exponent. So this is the P series. That is power series. Completely different things. Right. The next part, it will be a little confusing. But when we have an actual example with numbers, it will be less confusing. But for now, by the way, we did this in calculus 1. We call the linear approximation. So what we do is to estimate the values of the curve, we use the values on the line. Alright. So let me write so linear approximation. By linear we mean a line to estimate the curve. Loosely speaking, that's exactly what it is. So we have the graph here. So we have the curve, the function, and we're trying to use piece of x to approximate it. So here is the problem. Estimate f of x using a polynomial piece of x. And this one is a linear function. And what we have is we are given this condition. Derivative, the function the actual function and the linear function are equal at a, and derivative is equal to derivative at a. So the linear function and whatever the curve is, whatever the function f of x is, they have two things. The values are the same, derivative are the same. Right. Like I said, it will be kind of confusing when we write like this. But when we have numbers, it will make a lot more sense. Alright, so we start with with the derivative being equal. So step right like that, we say the derivative of that polynomial is equal to, because this is a linear function, it will be equal to that. But now here's the confusion part. We only substitute a on this part. Then you say, why don't we put a here and don't put a there? Right, here's why. Because it is linear constant. Linear function derivative is a constant, right? Like if we have the function like 2x plus 1, taking derivative of that is 2, is a constant. So the derivative is a constant, so that's why we just make that equal to a constant. Right. Now to get rid of the derivative, we integrate. By the way, this is also p prime of a. So when we integrate, we have because that is a constant. When we integrate, integral of a constant is that constant times x plus c. Right? Now, at x equal to a, I'm going to put a in here and in here. And to solve for c, to solve for c, we move that to the other side. And this is what we have. So after this, we can substitute this part back into c. So p of x equal to f prime of a times x minus f prime of a times a plus pa. So f prime of a, factor out x minus a and p of a. And f prime of a is equal to p prime of a. By the way, we did this in calculus 1. This is called linear approximation. By the way, I'm sure this one is a lot more confusing than what we have in Cal 1. Like I said, it will be a lot easier if we just do that with the actual problem. instead of using the formula, because writing like this is extremely confusing. So the point here is when we go to see quadratic approximation, quadratic approximation is, instead of using a line for linear approximation, quadratic, meaning that we'll use the second degree polynomial. And I'm not going even do that here, because like I said, given that condition, it is extremely difficult, extremely confusing if we try to derive the formula like that. But if we do that with a particular example, it will be a lot easier. So let's look at this first example here. You will see. Right, like I said, it is confusing if we do that in general case. For particular numbers, particular problem, it will be fairly simple. So we have that. Now in this problem we will find the first part, find linear approximation, meaning equation line, and next we have quadratic approximation. Right. Just need to go back to the previous one. When we call the function to approximate that, if it is linear, meaning the first power, we're going to use 1 subscript 1 to denote that. We use the linear approximation. Quadratic approximation, that is p2 of x. p3 will be a cubic function, and so on. Right. So we have that. Right, let's look at the first part. Oh shoot. There's a typo there, sorry. When I type it, I didn't recognize. Find the linear approximation for f of x near x equal to 0. That is the big mistake. It cannot be 0, so please change that to 1, because ln of 0 is undefined. Yeah. So it should be 1. It must be something other than 0, otherwise we cannot do it. Right, so we have to know where we are given the point x is equal to 1, or we can say a equal to 1. This is the center of the approximation. So whatever the point near it, that called the center of the approximation. Alright, now while we know the center, we know the function, the first thing we do is find the values and the derivative. So f of x equal to ln of x. So if we put a into it, f of 1 is equal to ln of 1, which is 0. Now we'll check the derivative of ln of x is 1 over x, and when that x equal to 1, derivative at 1 right. So because this is linear, we're going to do 2, because linear kind of mx plus b, right? This is even back to grade school. A linear function is mx plus b, so there are 2 coefficients, m and b, so we need 2 of them. Right. Now, like I said, it is very confusing when we do it like this, but will be much less confusing if we do it with numbers. Now, so we're going to find p of x. That's the linear approximation. And put the subscript 1 to denote that this is the linear function. Because of linear, that's why we have that number 1. Quadratic be 2, cubic 3, and so on, which is the highest degree of the function. Alright, so we use that to estimate. If we estimate, what we have to have is the derivative of that at equal to 1 have to be equal to 1. And the values of the function have to be equal to the derivative. I mean equal to the function, equal to 0. Alright, I try not to write like that, even though it's true. This is not that. What we have is we're trying to find that function, but first the derivative is equal to 1, equal to the derivative. Now we integrate. If this is the derivative, get back to the function by integrate that. And integral of 1 is just x plus c. Now, we're going to substitute in at the values. At x equal to 1, put 1 in for x. and p of 1 is just equal to f of 1 equal to 0. So 0 equal to 1 plus c, so c equal to negative 1. And substitute this in here. So p1 of x equal to x minus 1. So that is the linear approximation. Right? So we start with derivative and then integrate, and that will always be the case. Right? I said when we have the numbers, it is easier to work with than having in general. Next, and after this we even have a nice parent that we don't even have to do any of this. Find the quadratic approximation for f of x near x equal to 1. Once again, we have to change to 1, otherwise it doesn't make any sense. Right. Now this is quadratic, meaning that we're going to find something like ax squared plus bx plus c. So that's why we use the second degree polynomial as quadratic. Right. Now because we have the x squared on the second degree, we're going to need the function and the derivative. Alright, so first the function is ln of x at x equal to 1 we put 1 in for x, ln of 1 is equal to 0. And just like last example, we're going to make this equal to we're going to make that equal to p2 of 1. The values of the function will be the same as the polynomial. So that's the first one. Next we'll take the first derivative. And then we're going to put 1 into it. Put 1 into x. And this is the derivative of the function. We'll make the same as the derivative of the polynomial. I should write like this instead of writing that. That's just confusing. And then I will take the second derivative. By the way, in order to take the derivative of this, it will be a lot easier if we say x to negative 1. So when we take the derivative of x to negative 1, it is negative x to the negative 2, which we can write as negative 1 over x squared. Now when x equal to 1, second derivative so that is negative 1. Put 1 in for x, and that's what we have. and we will make it equal to the second derivative of the polynomial at 1. So if we want linear, we need the function and derivative. Quadratic go up to the second derivative because the 2 and the second derivative. If we want the cubic, we have to do the third derivative because the third derivative and the cube power, that is the third degree. So whatever the degree polynomial, we have to do the same derivative, right? And then we work backward from the bottom to the top. Bottom to the top. First, the second derivative is equal to -1. We work from the bottom to the top. And to solve for it, we'll take derivative. Antiderivative. From second derivative to the first derivative, just integrate. Much easier, just put the numbers into it. And integrate -1 is -x plus c. Right, so we start with the second derivative and work our way up to back to the function. Now, for second derivative, when x equal to 1, the point that is given, I'll put 1 in here. And then the derivative at 1 given to be 1. So we have 1 equal to -1 plus c. So c is equal to 2. Substitute that back in there. So now we have the derivative is equal to -x plus 2. Start from the second derivative, integrate to get the first derivative. Now to integrate one more time, we get back to the function. So that gives us integral of x is x squared over 2 and then plus 2x plus another constant c. This c is different than that c. Right, so pretty much that. Then we put in the point at p equal to 1. I'm going to put 1 in for x. And what do we say this value is equal to? Back when we said we did that for the function, that is equal to 0. Let me zoom out a bit. Earlier we did say that the values of the function of p of the approximation is equal to 0. So this is equal to 0. So we have 0 equal to negative 1/2 plus 2 plus c. So what's c equal to? Positive 3/2. Negative 3/2, sorry. Yeah. And then with this, you will substitute back into that c. And we have sorry, this should be at x equal to so finally we will have p of 2 of x equal to negative x squared over 2 plus 2x minus 3/2. So start from the second derivative, integrate, and then get the first derivative, integrate again, get back to the function. Right, let's take a 5-minute break here. We will continue at 10:12. even though that might be still a little confusing, but zoom back in 8%, right? Right. Now, Taylor polynomial. So Taylor polynomial, or later on we'll call this Taylor series. This is the theorem that will help us to estimate the function. So we need to do is there's some certain pattern to it, and we don't have to worry much about anything else. Right. So. Right. So let f be a function with the first derivative, second, third, and so on, up to the n degree, the n derivative. Defined at the point A. The nth order Taylor polynomial for f with its center at A. Denoted P sub n has the properties that it matches f in the values, slope, and derivative. Up to nth derivative. At A. That is, of course, when we say it matches the values, that's exactly what we said before. The function equal to the polynomial at A, the first derivative equal to the first derivative, second derivative equal to second derivative, and so on. Now we just have the formula, and this formula is proof similar to this. So just start with the n derivative, integrate, get back to the one less derivative, and just keep integrate until we get back to the function. With that, we have the nth order Taylor polynomial center at A is So start with the function derivative. Second derivative over 2. By the way, 2 or 2 factorial is the same. Let me write one more so you get the idea. If we have the third derivative, we divide by the 3 factorial. And then you get the idea. For the n derivative, divide by n factorial. Right? So the reason of that is, as you see, we keep integrating. So let me this. Okay, I'll get back to this real quick. So if we have that, and if we have to integrate this, if we have to integrate the result here, and that is the same as and the rest, so we have 1 over 6. So that's why we go from 1 2 factorial. 6 is 1 times 2 times 3. If we have to integrate this again, we have 1 6, and that's x to the 4th over 4, and then we just keep 1 over 24. So 2 factorial, 3 factorial, 4 factorial. So we just, every time we integrate, we divide by the numbers and multiply that too. That's why we have the factorial. So that's why we have this kind of long-winded. And we can just make it in the short hand version, and we say that, I think it's write that in the next line, or we just say piece of n of x equal to sorry, that should be k. And where c of k is equal to that. And this is for k by the way, even though that sounds complicated and all, but when we do this in the systematic table, I hope you get the idea. So this is very important. I'm sure if you go to any science, not much science, I mean, if you go to especially engineering, and definitely you need to know how to do this. This is the fundamental thing. I guarantee this type of problem will be on the test and will be on the final, because those are only the few things that I try to focus in this section. That. By the way, later on we call this as a part of the Taylor series as well. So same old formula, very important. Need to know that. Keep that for now. Right, let's look at the example. So I'll find the Taylor polynomial of order n equal to 0, 1, 2, and 3 for the function. Now do something very simple, e to the x, and that is centered at x equal to 0. So that's the first part. And then use the third degree polynomial to estimate e to the 0.1 and find the absolute error. We could potentially did like what we did at the beginning of the section, take the third derivative and then just go back up, but systematically this is how we're going to do it. So I didn't do this in Calc 2, that's why I forgot the thing. So we're going to make a table like the one we have over there. We have k. K will take the values from 0, 1, 2, and 3. And then the next one, we just have the derivative. For x. And then the next, we have the derivatives, I should say, when x equal to a. And finally, we have the coefficient. Right. When we get used to this, is we will do actually a bunch of this, and so to get the idea of what this is about. So the function is f of x equal to e to the x. So original function is just e to the x. That's what we start with. Now let's put the values of this in here. In our particular problem, a is equal to 0. So here a equal to 0. So what we do is we're going to put 0 in for x, which is 1. And after that we take that number, divide by k0 factorial. So what is 0 factorial? I just want, it is 0, is 1 by the way. I just want to show real quick. Second, no, not second. Just hit math, go to here, probability number 4. Right, so 0 math factorial, and that is equal to 1. So 1 over 1 is equal to 1. Easy, right? So when k equal to 0, we just have the function at values divided by factorial. Next, when equal to 1, that is the first derivative. Luckily, this one derivative is still that. Derivative of e to the x is e to the x. Now we're going to put in the values in for x. 0, which is 1. Next, we take that values, divide by factorial. 1 factorial is still 1. That's what we have. Next, for 2, that is the second derivative. Happen to be the same thing. Now we're going to put 0 in for x. It just happened to be the same one. And then whatever the values is, divide by k factorial, which is 2 factorial. 2 factorial is 2 times 1, which is 1/2. Then we take the third derivative. Happen to be the same one. And then put in 0, still 1. And then 1 over 3 factorial. Right. Okay. Alpha no, sorry, my calculator did not get to that. It only it did not get to that on my calculator. Maybe the newer one can that. But anyway, that exclamation point for factorial math on my calculator, go to math, probability tab, option number 4, right? Or we just multiply backward. So that's simple enough. Yes, the one with the color addition certainly can do it. Yeah, I don't have it. Why do I? No, I don't have it. By the way, I do send you the link for the TI calculator way back at the beginning of the semester, so you can install the calculator on your computer. Anyway, so it's not that bad, right? The concept is easy. Derivative, evaluate the values, divide by factorial. We start with the function, first derivative, second derivative, third derivative. The only problem is when the functions are complicated. Yeah, when that is the problem. Right. Now, but we do have those numbers, right? It's not that bad. Right. Now, what do we use with those numbers? Right. Now, the question asks us to find the Taylor polynomials of order 1, 2, 3, and order 0. So, this is how we write the answer. It's right there already. the first one is going to be the first number. That's it. Now, for P1, we're going to have the first one plus that. So this one is that, and the second one is this one, x minus 0. And then P2 of x, we have 1 and then 1/2 x minus 0 square. And then P3, 1 plus 1 1/2 x minus 0 square plus 1/6 x minus 0 cube. So you get the idea, right? The coefficient, if the first degree the 0 degree polynomial, we have 1. First degree we have 2. Second degree we have 3. Third degree we have 4, and then so on. P4 will be 5 of them, and we just keep going with this. By the way, when we increase the power, because this one center at 0, so that's why we subtract the 0 here, because that one center at 0. But x subtract 0 is just x, so we have 1 plus x, 1 plus x plus 1/2 x squared, and this will be 1 plus x plus 1/2 of x squared plus x 1/6 of x cubed. And we can go further if we want to. So make sure you know how to do this table and how to put that information on the table into the polynomial. Usually later on we don't worry about the first three, we just worry about that. But in this case they asked for it, so there it is. Right, like I said, this is the most fundamental thing. If you can only memorize one thing in this chapter, it will be how to do this table. Right. The next part is how do we do this to evaluate. Right. So very simple. Now we have P3 of x is equal to this. Just copy from one line to another. And we estimate at 0.1. So at x equal to 0.1, P3 of 0.1 equal to. So we just put 0.1 store into x, and I'm just going to enter this function 1 plus x plus 1/2 x squared plus 1/6 x cubed. So I have that. Right. And find the actual values. What would, so this is approximation using the polynomial. The actual values, this is the actual values. So as you see, the approximation is extremely good. Could say up to 5 decimal places. So the absolute error. Just subtract these two and take the absolute values. So all I do is take this number, subtract that number, and we have negative 4.251 times 10 to the negative 6. So that's extremely accurate. No, A is not always 0. A could be something else. As you see in the next one, we do A equal to pi over 4. Yeah. So the center is not always 0. It is 0. I choose the first example, so it is similar to do, but it could be more complicated. Right. Talk about more complicated. The next example, but the idea is we still have the same table though. I said, the ability to do this is very important. You will see this on the test and you will see this on the final. Find the 4th degree polynomial that approximate f of x equals sine of 2x near x equal to pi over 4. So in this case, that is A. So it's not equal to 0 anymore. So the calculation will be slightly more complicated. Right. But we'll make the table the same way though. So 0, 1, 2, 3, and 4. This one to the 4th degree, so we go up to 4 on the table. Right, the first one is the derivative. Next one is the values. And finally, whatever that value is, divide by factorial. Right. So derivative or the function, and then evaluate at the point A. In this example, A is pi over 4, and then whatever we have there, divide by factorial. That will give us the coefficient. Right. First, the function is sine of 2x, and then we will take the values put in for x. Sine of 2 times pi over 4, which is sine of pi over 2, which is 1, right? Sine of 90 degrees is 1. And then we have 1 over k0 here, 0 factorial. 1 over 1 is equal to 1. Right, that is the function. Now we take the derivative. Right, the derivative of sine is cosine, but then we have the numbers. So just 2. When we learned about integration by parts, we did use this. It's cosine. Dang it. So if there's something times x, just bring that outside. It's only coefficient times x. If we have sine of x squared, have to use the chain rule. This is also the chain rule, but the derivative of 2 to x is 2, so that's why we just have that. Now we're going to put pi over 4 into x. So we have 2 cosine of pi over 2. Cosine of pi over 2 is 0, so this is 0. And then we'll take that, divide by k factorial, which is 1. 0 divided by 1, 0. Right? Now we'll just take the derivative again, which gives us second derivative. The derivative of cosine of 2x is negative 2 sine of 2x. The derivative of cosine is sine. However, there's 2x, so there should be a 2 times it. So negative 2 sine x, and multiply together, negative 4 sine of 2x. Negative 4 sine of 2 times pi over 4. So negative 4 sine of pi over 2. Sine pi over 2 is 1. Right? So negative 4 times 1 is negative 4. We will take that number, divide by 2 factorial, because k now is 2. 2 factorial is 2 times 1, so this is just negative 2. It's not that bad, right? Just check the derivative and then evaluate and then divide by factorial. Now, third derivative. Negative 4. Derivative of sine 2x. We did this already. 2 cosine of 2x. That gives us negative 8 cosine of 2x. Now we're going to put pi over 4 in for x. Negative 8 cosine of pi over 2, because pi over 4 times 2 is pi over 2. Cosine of pi over 2, cosine of 90 is 0. And we're going to take that values, divide by factorial of k. 0 divided by anything is 0. Right, fourth derivative. We're not going to just write fourth line that too much. And then we have negative 8 derivative of cosine of 2x. Negative 2 sine of 2x. So negative 8 negative 2 will be 16 sine of 2x. Now we're going to put 2 in for x. Sine pi over 2 is 1, so I have 16 times 1 is 16. And we will divide by 4 factorial. Right, 16, 4 factorial will be 4, 3, 2, 1. So 16 over 24. Which is 2 over 3. Right, so it's not that bad. Function, derivative, second derivative, third, and fourth. So that's the tricky part. The easier part, put in the values, and then just divide by factorial. So those are the coefficients. So after that, we just write the answer. Now this is the fourth degree polynomial. Start with a number, and then we have that coefficient, and then x minus the center, and then plus we have negative 2, x minus the center square. And then we have 0, x minus the center cube, and then 2/3, x minus the center 4th. Of course, 0 times anything is 0. So this simplifies to 1 minus 2, x minus pi over 4 square, plus 2/3 x minus pi over 4 to the 4th, and so on. Oh, wait a minute. No. This is a polynomial, so that's where we start. It's not that bad, right? Function, derivatives, and so on. Put in the values, then divide by factorial. Those will give us the coefficient in polynomial. Taylor polynomial. Right. Now we go to more of the theory of it. So remember in Taylor polynomial. So let P of n be the Taylor polynomial of order n for f. The remainder in using the polynomial to estimate. At the point is R sub n equal to f sub x minus p sub n plus x. So pretty much what we did earlier is when x equal to 0.1 we find the absolute error. So this is kind of the absolute not the absolute, just the error. Right. B. Taylor theorem. Yeah, so the Taylor, this method give us the coefficient at the n degree polynomial, and the Taylor theorem give us the remainder. Let me write it down. Then for all the point in the interval, the actual values of the function, we just add that to the other side. Of course, there's no big deal, we just add that to the other side. But the big deal here is this, the formula for R sub n. Now this important things about this theorem is this: the remainder terms, the error, the difference between the actual function and the approximation is n plus 1 derivative. There's a typo that there's no c in the formula, there's just a. Oh wait, never mind, there's a c. So there's no typo here. It should be something other than A. And that is the point between x and a. let's just write all the theorem here and then we'll continue next time. So pretty much say that if that term is equal to m, and so n of x equal to the absolute error be less than equal to m over n plus 1 factorial x minus a n plus 1. So pretty much what we do is, if we just replace this by m, and we not just replace it by m, we replace that with the upper bound. So m is actually, it's going to be bigger than that values. If we replace that, we have this term. Right, so we're now out of time, so we have to stop here. And then so we can pick it up on Friday. Right, of course we will do a lot. If you look through the note, we have a bunch of those tables. Not in the next section though. So we have those table again. So one of the most important things in this chapter is be able to do that table. So which is not much. It's not just got one, right? Derivatives. Right. So do you have any question before I end the stream here? Right, the next test, I have the review already, but did not post it. The next test is up to the end of this chapter, so 11.4. Right, so the test will be from 10.5 to 11.4. And I have the review this weekend, and the test will be posted right after that. But we should finish chapter 11 by Monday, so we should be able to take the test 3 on Monday, and then after that the final should be on Friday. Right, if you have no question, I'm just going to end the stream here. So today I used the Wi connection instead of the Wi-Fi, so that's why I don't think there's any lag at all. So I probably keep using it. Right. Did yes, you just whenever you finish. By the way, there's a deadline for it, right? The extra credit assignment, it is due yes, due on the 13th. So next Wednesday, you're gonna before 11:59 p.m. you just turn it back to me for extra credit. Right. No, that assignment is on paper, not on paper, on the Word document. You just open it up and type your answer directly on it. You don't have to go to any website at all. Do you have that? By the way, I remember now, when I sent out the email about all the course information, I did attach that assignment to it. So just open that, and then you have to end. I think click on the top to end. What do we do? Yeah, click on that to enable editing. I think, yeah, and then you can type your answer directly on it, and then save it as either PDF or Word document and send it back to me. Right. So that is the deadline of the core artifact assignment. That is due at the earliest compared to the other. Everything else is due on Saturday night. Right. So that would be it. Right. So the final exam, probably about 20 questions. You have 2.5 hours for the final. So just like pretty much like those tests, but all of them are multiple choice.